Hello everyone, I'm Ella and I'm an aerospace engineer with Team 26071. We are working with Northrop Grumman to design a hypersonic projectile that focuses on maximizing range and minimizing cost. Our sponsor is Rob Esslinger of Northrop Grumman and our mentors are Dr. Raymond Mose and Dr. James Threadgill.
My name is Brianna Curley and I'm the team's electrical engineer. We are now ready to get into some of our system requirements for this project, among the most important of which, the system shall be launched between a speed of Mach 5 and Mach 8, shall be aerodynamically stable in all three axes, shall have an internal temperature of no more than 74 degrees Celsius, shall impact the ground at least Mach 2, shall be able to carry a payload with a fixed mass and a fixed size, shall be no longer than 1 meter in length and 0.2 meters in diameter. And finally, the system shall not be powered by an additional boost vehicle during the cruise.
So why does this project matter? Because hypersonics is one of the most rapid advancing areas in the aerospace industry with civilian and military applications, as well as because of our low altitude regime and our high speed, we are currently breaking ground in the hypersonic design.
Over the course of this project, our team has faced many challenges, from a lack of publicly available hypersonics resources, to having to coordinate collaborations across multiple time zones, to having to build technical knowledge in the field from the ground up. In spite of these challenges, we have succeeded in creating a satisfactory design and building meaningful connections both within and outside of our team. Our product will have a profound impact on future hypersonics endeavors, and it will serve as an example to those who come after us of just how much can be accomplished by ordinary university students within a single year.
Here we have the geometry of our vehicle, which is an LD-HEC body, which is a body meant specifically to minimize drag at hypersonic speeds. It has a hexagonal cross-section right here with fins on the top and bottom and control surfaces on the diagonals, which helps us maintain control authority through our entire flight while remaining inside of our geometric constraints. The tip on the front is made out of tungsten with a boride coating to help both mechanical and thermal survivability as well as oxidation resistance, and then the main body is made out of 304 stainless steel. Here we have our interior cross-section, starting with our tungsten nose, our aero guard insulation from ProMat, our electronics, our payload, and finally our control surfaces and actuators.
Hi, my name is Logan Wilkie. I'm a sole mechanical engineer on the project, and I performed all of the thermal analysis. Due to our intense flight regime being of a low altitude and a high speed, there is ridiculous amounts of aerothermal heating entering our vehicle. Because of this, we needed to perform thermal analysis on our vehicle to make sure that our geometry met the specific UCO requirements given to us. Going into our thermal results, first we're going to look at a graph showing our heating along the chord length. Initially, we see a heat temperature of about 2,600 degrees Celsius during the first 2 seconds, followed by an immediate decrease in temperature, ending at around 200 to 300 Celsius at the tip. Obviously, heating was drastic there. Next, we're going to go to our sample wall temperature. This is at 700 millimeters on the length, near where the cabin is. We have a material stack of Inconel stainless steel and air guard insulation. As we can see, the heating will go very slowly through the insulation, leading to a final internal temperature of about 42 degrees Celsius, about 30 degrees less than our requirement.
To maximize the range of our system, a trajectory code was formulated as shown here using lift and drag tables from NASA wind tunnel testing data. And we began with the 45 kilogram projectile being released at Mach 8 at 14.5 kilometers. And the projectile then flies horizontally at a constant flight path angle for a certain amount of time before a pushover maneuver is then initiated at pitch 1 as seen in the diagram. The code then performs a series of modulated pitch maneuvers while simultaneously modulating angle of attack until ground impact at Mach 2. The code changes the time the projectile flies horizontally to maximize range while still meeting our release and ground requirements. The code formulation was then updated to include a 15G maneuver to fulfill our requirements of the system. The projectile is still released at 14.5 kilometers at Mach 8 and then begins banking at an angle of 86.6 degrees, which is where the 15 Gs of force is applied to the vehicle. This occurs right at the start, about here. This plot shows our results for holding the bank angle for times of 0, 2, 4, 6, 8, and 10 seconds. Our downrange varies from about 125 kilometers to 160 kilometers, with the furthest range corresponding to no bank angle.
Hello, my name is Enzo, and I am majoring in aerospace engineering. I am in charge of all of the CFD analysis. SU2 is the program that we use for CFD. In order to run that CFD program, we have to create a mesh from a different program called GMesh. Once we finish running the simulations on SU2, we use another program to visualize those results using ParaView. And here is our CFD results from the SU2 program. On the top right corner, you can see our Mach contour at Mach 8 at 0 degrees. We've also generated two graphs, which are the lift coefficient versus angle of attack graph and the drag coefficient versus angle of attack. On this slide, we have another Mach contour graph with a different angle of attack. We also have an L over D graph and a drag polar graph. In the L over D graph, we can see that our CFD data and the NASA benchmark data are in very close comparison, and we see our max L over D at around 8 degrees.
For the control surfaces, we need to maintain static stability for our hypersonic projectile. We have three different axes we need to focus on: the pitch axis, the roll axis, and the yaw axis. For our design, we have four different control surfaces at the end of the projectile, and they will each be deployed at a different deflection angle in order to maintain static stability. While designing the control surfaces, I needed to change the size, shape, and the center of gravity location. For the control surfaces, we have four flaps deployed by actuators towards the back of the vehicle, as well as two vertical fins. These will help us perform the 15G turn. Each of the flaps are 136 by 60 millimeters in area. They can also be deployed a maximum of 10 degrees in order to get us good control authority. After sizing the control surfaces, we then can sum the moments around the center of gravity using shock expansion theorem and produce a pitching moment versus angle of attack. Here it can be seen that each colored line is a different deflection angle of the control surfaces. We can see that it is a neutrally stable because the slope is around 0 for the lines, and we are usually stable for the pitching moment. For the yawing moment, we have a positive slope, which means that we are actually statically stable. And for the rolling moment, we have a negative slope, but this also means that we are statically stable. In summary, we are stable in all three axes.
Hey, welcome to the University of Arizona's in-draft supersonic wind tunnel. This is a high-speed, vacuum-driven wind tunnel with very large vacuum take outside that gives us about 15 seconds of runtime. We can run at speeds of Mach 2.3, 4, or 5, depending on the nozzle we have installed. Here you can see our model mounted in the test section on a sting. This gives us a good view of what's going on in our flow field using our Schlitter imaging, which uses this light source, along with one and another spherical mirror on either side of the tunnel, reflecting back to a high-speed camera. We can also use thermal imaging to get an idea of the thermal loads going on during our experiment. Thanks for coming by, but we're going to get back to testing.